Hi everyone, welcome back. So let's continue and talk about surface integrals of vector field, the flux of a vector field across a surface. Okay, so do you still remember when we talk about in R2? So in R2, we have circulation and flux. What's circulation? So circulation, we also call it flow, or we also call it work done, right? And that we want to measure how much vector field are going in the direction of C. Okay, so how we calculate? We use the line integral f dot dr. And in R2, what is the flux? Well, flux, we want to measure, let's say this is the orientation of the curve. We want to measure how much the vector field are across the curve from left to the right, right? So this is in R2, okay? So the flux integral was f dot n is the normal vector that we define, and be t cross k, right? ds. That's the flux. And this is in R2, okay? In R3, well, in R3, we can also talk about the circulation of flow. So in R3, we can still have this curve is now in space. We can talk about the vector field going in the direction of C. But however, for the flux, well, you cannot talk about the vector field going across a curve, because perpendicular to the curve direction, there are a lot of vectors that are perpendicular to it, right? You can say going across a curve in space is not defined. So in R3, when we talk about flux, we're talking about the vector field going across a surface instead of a curve, okay? So flux is vector field. So in R3, flux integral is the vector field going across a surface. Okay, so going across a surface, then this is defined. So far, so good? Okay, so first let's talk about oriented surface. On any given point on a surface, the unit normal vector points in one of the two possible directions. So we can pick an orientation of a surface, meaning we can pick a direction for the normal vector n. Let's say at this point, we can pick this is the normal vector. So this cone is actually an oriented surface. Okay, because imagine you are like standing right here, and then you goes around the cone, and then when you come back, you still going on this side of the surface, right? But this example, this is a non-oriented surface. Why is that? So imagine you're standing here, and then when you goes around, then you are like at the back. Oh, how can I draw it? So you're on the back of the strip, and then you goes around, and then now you're top here, and you goes around. Then see, you're at the back of this guy. So it's like your orientation flip. Okay, so this is non-oriented surface. Okay. So the flux of a constant vector field along a flat surface, let F be a constant three-dimensional vector field. Let S be a flat surface with a specified orientation for the unit normal vector n. We define the flux of the vector field across the surface be the following quantity. We use F dot n times the area of S. So if we interpret F as the velocity field of a fluid, then this quantity of flux represents the volume of fluid that flows across the surface S per unit time. Okay, so see, this is a picture how we want to measure how much the vector field are going across the surface S. Okay, So flux is the volume of the fluids passing through surface per unit time. Note the following. The area of S matters when computing the flux. Of course, if you have a larger area, then the more fluid going through it compared to this small area, right? And then second, the angle between F and N make a difference as well. Because think about it. If we have the same size, but I want to make the same size, but one, the vector field goes like this. The other one, the vector field goes like this. Of course, this guy, we have more fluids going in, right? Passing through the surface. So the angle make a difference. So that's why we have F dot N, okay? N is the normal vector of the surface. So F dot N is the magnitude of F and the magnitude of N times cosine theta. So far, so good? Okay. Now, let's look at the following picture. Okay, so keep that in mind. First, when theta is 0. Okay, so this is the direction of our normal vector, right? And when theta is 0, it means, how does our vector field look like? Is parallel to the normal vector, right? Okay, so F flows across the surface in the direction of N. How about when theta equals pi? Well, when theta equals pi, then they're opposite direction. So F flows across the surface in the direction opposite to that of N. How about theta equals pi over 2? Ooh, see? F is gonna flow. None of the F flows across the surface at that point. They're orthogonal. Can you imagine, everybody? Okay. General situation, flux of a vector field through a surface. So how can we define the flux of a field? So which is not necessarily constant. We might have a curved surface, which is not necessarily flat. Well, the idea is we can partition the surface into small surface patch, and if the patch are small enough, they are approximately flat, right? We can use the tangent plane at that point to approximate it. Then the field is approximately constant on each of the little patch. So across each surface, F dot N is a scalar value function. Here's a place we need the parameterization. Okay, so we talk about the parameterization of a surface as. Then how do we find a normal vector? Well, we know a normal vector is TU cross TV, right? And we assume to be consistent with the orientation of S if we have an oriented surface, okay? Then the unit normal vector is, well, we know this is a normal vector. Let's divide it by the magnitude of it. So now this is the unit normal vector. So flux on the patch equals to, well, this is the scalar component of the vector field in the direction of the normal vector, right? So that's why we use F dot N times the change of the area, the surface area. So that's why the flux across the entire surface, we add those little pieces up. So we have the limits. The surface area differential goes to 0. We have sum those F dot N times change of S. Okay? Yes. So, and what is N? N is, well, N is the cross product over the magnitude of it. But last time we talked about the surface area differential equals the magnitude of the cross products times change of U, change of V. And then now, see, this is cancel. So we only have F dot the cross products times change of U and change of V. So this is the flux. Okay, So let U be a continuous vector field, and then on a region that containing a smooth surface S, given parametrically by R of UV, where D is the region in the UV plane. Assume that the tangent vectors TU and TV are continuous on D, and the normal vector n equals TU cross dTV is non-zero on D. Then the flux integral of F over S is then the double integral on the surface F dot n ds. Okay. I want to remind you in R2 the flux integral was over surface F dot n ds. Well, this is small s. This is small s. It represents the at-length parameter. And here, this is a big S. It represents the surface differential, surface area differential. Okay, and that equals, oh, I think I have a mistake here. So n is, I forgot about over the magnitude, so let me fix it. So n is the unit normal vector in this case. Okay, so that's why we know, and we have the magnitude in the bottom, and then the surface area differential. We also have the magnitude. The magnitude of the cross product cancel out, so that's why we just have F dot TU cross TV, and then dA is the area differential. It could be, so dA is du dV or dV du. It depends, the order depends on the situation. Okay, if our domain D, the D in the UV plane is a rectangle, then the order doesn't matter. But if U is a function of V, then we have to have the order du dV. The dV is outside. Or if V is a function of U, then du is outside, dV is inside. So far so good, everybody? Okay, let's do some examples. Example. Let S be the portion of the cylinder x squared plus y squared equals 4 in the first octant, with Z is less than or equal to 3, oriented outward, away from the z-axis. Compute the flux of the vector field 0, y, 0 through the surface. Okay, so let's draw the picture. So cylinder, well, the radius is 2. In the first octant, then we have to restrict, right? We restrict into these pieces. With Z is less than or equal to 3, let's say this is 3. So this is the pieces. So far so good, everybody? Next, compute the flux. Okay, so first we need to find a parameterization for this surface, right? So because we have a cylinder, central coordinate r cosine theta, right? So let U be theta, right? And let V be Z, right? And then x is gonna be r, because r is 2, so r cosine u, r sine u, z is v. So our parameterization, r of uv equals 2 cosine u, 2 sine u, and v. Now, what is the u? U is like the theta, but we are in the first octant. So u is between 0 and pi over 2. So far so good, everybody? And z is less than equal to 3 and it's in the first octant, so 0 less than equal to v less than equal to 3. So far so good, everybody? So this is our parametrization. Next, we want to compute the tangent vectors. Well, then tu is derivative with respect to u. Cosine u, we get minus 2 sine u. Derivative of sine u is cosine u. Derivative v with respect to u is 0. tv, oh, those has no v, 0. The last one is 1. Okay, what is the cross product? So the cross product minus the first row is ijk. So minus 2 sine u, 2 cosine u, 0, 0, 0, 1. Okay, I, determinant of this guy, 2 cosine u, and then minus j, determinant of this, minus become plus, so 2 sine u, and then k times the determinant of this guy, 0. So far so good, everybody? So actually we have done something. Our previous example about surface integrals of a scalar value function, we have done this before. Okay, but before we continue and find the magnitude of it, here we don't need to do that. Okay, so our flux integral equals f. Well, f is 0. Y, what's y? Let's look at the parameterization. What's your y? 2 sine u, z 0. That product with this tu cross tv. So far so good, everybody? Alright. And here, let's look at our domain D in the UV plane because the rectangle, the order doesn't matter. Let's do dv du. V is from 0 to 3. U is from 0 to pi over 2. So that equals 0 to pi over 2, 0 to 3. Okay, you see? That product, 0 times that is 0. 2 sine u times 2 sine u is 4 sine u squared, and then 0 times 0 is 0. dv du. Okay, because it has no v, well, it means we just get v, right? We get v evaluated from 0 to 3, and then you know what is the 2 sine square? Well, keep in mind double angle formula. Sine squared is 1/2 minus 1/2 cosine 2u. When you multiply by 4, well, this is 2 minus 2 cosine 2u du. Okay, so we evaluate from 0 to 3. It's just like 3 minus 0. That gives us 3 in front, and then we have 2 minus 2 cosine 2u. The integral is 2u. Integral cosine is sine. But because you divide it by 2, right? So 2 divided by 2, they cancel. Evaluate from 0 to pi over 2. So that's 3. 2 times pi over 2 minus 0. And sine. 2 times pi over 2 is pi. Sine pi. And sine pi is also 0. Sine of 0 is also 0. So this is our answer. 2 cancel, and our answer is just 3 pi. So far so good, everybody? So this is the flux. It measures how much vector field go across the surface. Alright. let's continue. Okay. So here, let S be the upper hemisphere given by x squared plus y squared plus z squared equals 4. With z greater or equals 0, assume the orientation of S is outwards, away from the origin. Compute the flux. Okay. So what is that? Well, so actually this example for the parameterization, we have seen this surface before, right? In our last video. Okay, so let me let me go back. Okay, instead of do the whole thing over, let me go back and check our work with you. I hope you have seen the last video, did you? Okay, this is it. And this is our parameterization, right? But right now, because we have the top sphere, so the range of u and v gonna change, okay? But however, the tu plus tv will give us the same answer. So let me see. Let me how do I copy it? Okay, let me just copy the whole thing here. Okay, so I took a picture of it. And okay, so let me let's see. Oh, okay. Okay, let's see. Let me shake this a little bit. Okay. All right. So now here you can see the radius is also 2, right? So this is 2, but because the surface is the whole upper hemisphere, right? So our parameterization is gonna be 2 sine u cosine v, 2 sine u sine v, 2 cosine u, just like what we had before. But now our u is like the drop down angle phi, right? V is like the angle theta. And so u is now from 0 to, the upper hemisphere, from 0 to pi over 2. And then v is still from 0 to 2 pi, right? And then we have the tu. Okay, let's see. Let me, can I? Okay, so can I chop it? Oh, yes. So I can chop it here. All right. So, and then I can move it here. Let me also write it down that, so tu plus tv is, well, let's copy down, 4 sine u squared cosine v, 4 sine u squared sine v, 4 sine u cosine u. Okay, and then let me chop this again. Okay, because I don't want to have this picture is not the same as our picture, so I want to chop it. And oops, okay, and I want to chop more. the bottom. I don't need that. Okay. Alright, good. So now I just make this look bigger. Okay. So far so good, everybody? Alright. Great. Now we get TU and TUE, and we also get the cross products. Now we're ready to compute the flux. So the flux, can I move this a little bit? Yes, good. Okay. So the flux equals the integral F. F is 0, 0, Z. Z, look at our parameterization. 2 cosine U. Dot product. Oh, let's copy this guy down. 4 sine squared cosine V. 4 sine squared U. Sine V. 4 sine U cosine U. And then here, because U and V are both between two numbers, so the order doesn't matter. So let's do dV du. V is 0 to 2 pi. U is from 0 to pi over 2. Okay, what is the dot product? Well, the first two coordinate is 0, so, and we just get 2 times 4, 8. 8 sine U cosine U squared. Cosine U squared sine U. Why do I switch the position? Any guess? Yeah, and later on we can do U substitution. Yeah, because the derivative of cosine is related to sine U. It's minus sine U. Yeah? Okay, first, you see there's no V in there. Pull out the 8. And then we have cosine U squared sine U. Integral of 1 respect to V is just V from 0 to 2 pi. Well, it's the same as we multiply by 2 pi. So we can multiply by 2 pi in the front. We have 16 pi. And then integral from 0 to pi over 2 cosine square sine U du. So here the place we can do U substitution. But let's call it W, because we already have the U. So W is cosine U. Then dW is negative sine U du. Right? So this is 16 pi. Integral U W of 0 W of pi over 2 W squared. Sine U is minus dW. Minus, put it in front, dW. W squared integral is W cubed over 3. Evaluate. What's W of 0? Cosine 0 is 1. W pi over 2, cosine pi over 2 is 0. So 16 pi 3, okay, 0, oh, 0, minus, I'm talking 1, is 1, right? 1 cube is 1. Oh, minus become positive, 16 pi over 3. So this is our answer. So far, so good, everybody? Okay, so first, we realize this is a sphere. So for sphere, we learn the parameterization. Okay, we let U be the drop-down angle phi, let V be the angle on the xy plane, make with the positive x-axis, the theta. Okay, and then this is the upper hemisphere, so U is between 0 and pi over 2, and V is between 0 and 2 pi. Then we can take the derivative with respect to U and take the derivative with respect to V to find the tangent vectors. And the normal vector is going to be the cross product of TU and TV. And here, because we're doing flux, we don't need to compute the magnitude. Okay? So the flux integral is we use the vector field dot product with the normal vector, okay, TU plus TV. And then we can calculate the trig integrals, the double integrals. So far, so good, everybody? Okay, let's continue. Surface integral or flux integral on explicitly defined surface. So this is like just a special case. Okay, so suppose a smooth surface S is defined explicitly by z equals a function of x and y over a region D in the xy plane. Then we can have simpler formula for the surface integrals and flux integrals. So now we can consider the natural parameterization. Alright, so we have x and y, and then z is a function of xy. Right? Then what's tx? Well, the derivative with respect to x. Derivative of x is 1, derivative of y is 0. This guy is just gx, or we can call it zx, as you like. Okay? So partial z, partial x. And then ty, the derivative with respect to y. This guy is 0, derivative of y with respect to y is 1. And then we have partial g, partial y. We can call it zy. Okay? Then what is the cross product? Let me show you here. So remember, tx cross ty, we do I, j, k. And then tx is 1, 0, zx. Ty is 0, 1, zy. So what do we do? First, I component. Determinant of this guy, 0 times zy minus 1 times zy, so minus zx. Sorry. Yeah, 1, sorry. Determinant, right? So 0 times zy minus 1 times zx. Okay, and then we have the minus j component of the determinant of 1 times zy minus 0 times zx. But it's minus j, so we get minus zy. Is that okay, everybody? And then for the k component, determinant of this is 1. So we get, this is the normal vector, right? And then the magnitude of it is the square root of zx squared plus zy squared plus 1. Okay, so surface integral for function z equals so surface integral for on the surface that z equals gxy. Then let f be a continuous function on a smooth surface S given by z equals g of xy for xy in the region D in the xy plane. Okay, then the surface integral is, well, the double integral on the surface. Okay, that's, so here S is on the surface, well, D is in the xy plane, on the plane. Okay, and then we have F, and don't forget, well, this is the magnitude of tx cross ty. Okay, so square root of zx squared plus zy squared plus 1. And dA could be dx dy or dy dx. Okay, and then the flux integral for the surface, well, we have F is continuous vector field on a region of R containing a smooth surface S given parametrically by z equals function g of xy. Then the flux integral equals, well, we have the double integral on the surface, and D is the region on the xy plane. We have F dot. This is the normal vector tx cross ty. Okay, and we have dA. Okay, so with this, you can see this is simpler formula. So with this formula, let's find the flux of the radial vector fields xyz across the paraboloid. Z equals 1 minus x squared minus y squared. Okay, so first, what is our parameterization? Well, our parameterization is xy and then 1 minus x squared minus y squared, right? Okay, so zx, what's zx? Well, zx is 1 minus 2x. Zy is, sorry, I don't have 1. Just the derivative of minus x squared is minus 2x. Zy is then minus 2y. Right? And then what is the flux integral? Right? So by this formula, we know Tx cos Ty is then minus Zx, so 2x, minus Zy, 2y, and 1. Okay? So f is x is x, y is y. Z is 1 minus x squared minus y squared. Okay, so it really depends on the f, right? If the f say y, x, z, then what do? You switch your x and y. Okay, so is whenever you see x, oh, that's the x coordinate of our r. Oh, it's x. Y is the y coordinate of it is y. So z is the z coordinate of our parameterization. So far, so good, everybody. And then we dot products with, this is 2x, 2y, and 1. And let's see. Oh, we still need to figure out the x and y. Let's draw a picture. This is a paraboloid. When z is 0, we get x squared plus y squared is 1, right? So that's the unit circle. When x and y are both 0, we get z equals 1. So this is the paraboloid. And z is greater or equal to 0. Oh, so we know x and y is in the circle. So we can do, let's see. Let's put dA here. And here, let's put d. Let's simplify and see what happened. Okay, and here, dot product, x times 2x, 2x squared, y times 2y is 2y squared. Well, and that times 1 is 1 minus x squared minus y squared, dA. Okay. Wow, what do we get? 2x squared minus x squared is x squared. 2y squared minus y squared is y squared. Ooh. See, here it's much better to use polar coordinates. Okay? Yeah, now we just get a double integral. Right? For a double integral, we can use polar coordinates. So, use polar coordinates here. Otherwise, if you want to use a rectangular coordinate, you have to let x goes from -1 to 1, and then your y your y, so x is from -1 to 1, and then your y will be from minus square root of 1 minus x squared to 1 minus x squared. So this is more complicated, isn't it? So let's use polar coordinates. That's why you see here I didn't put like x and y bounds there, okay? Because maybe later on when we use polar coordinate, it can simplify our answer. So if we use polar coordinate, x squared plus y squared is just r squared, and then dA is r dr d theta. By the way, don't forget the parentheses. Okay, if you forget the parentheses, then you just have r squared plus r. This is not good. When you distribute it, we should get r cubed. So far, so good. And r is from 0 to 1, right? The unit circle. Theta is from 0 to 2 pi. Yeah, much easier, isn't it? So we distribute r cubed plus r dr d theta. Integral of r cubed is r to the 4 over 4. Integral of r is r squared over 2. Evaluate from 0 to 1. So we plug in 1. We get 1 over 4 plus 1/2. When we plug in 0, it's just 0. Ooh, this is just 3 over 4. And when you integrate a constant with respect to theta, it's just theta. And when we plug in 2 pi, we just get 2 pi. So it's like 3 over 4 times 2 pi. So the answer is 3 pi over 2. So this is the flux integral. So far, so good, everybody? Okay, any questions? Some of you might ask, oh, do I need to memorize this formula? What if I don't memorize it? It's okay. If you don't memorize it, just derive it. You know the parameterization, right? Then you can figure out your tx and ty easily, and then compute the cross products to get this answer. So you can still use the old way to do it. So far, so good, everybody? Okay, so now we have talked about the flux integral. Okay, for in the R3, it measures how much vector field go across a surface. Okay. So two-dimensional flux is just a line integral. The flux integral is just measure how much vector field go across a curve. So we have a single integral. But in R3, the flux integral is like how much vector field go across a surface. We need surface integral. This is a double integral. Okay, so please go ahead and do your homework. If you have questions, feel free to ask me. Cheers! Bye!